All right, welcome back, everybody. This is the last session on stage two. So we're switching away from software, looking at something to do with propellers in the dry docks. I will let our speaker, Adam Kaplan, who is the Chief Technical Officer of True Prop Software, take you through that. So over to you, Adam.
Thank you. Thank you for that introduction. And hello, everyone. Good morning or good afternoon, depending on where you are. Thanks for watching. So today I'll be talking about how shipyards, boat builders, and dry dock operations can leverage new technology to more easily assess the condition of a propeller. And I think everyone intuitively knows that the propeller has a major influence in ship performance. Top speed and bollard pull, engine load and fuel efficiency, cruising RPMs, they are all driven by the torque demand uh, and thrust produced by the propeller. Intuition also tells us that a geometrically precise and well matched propeller uh, will outperform a damaged propeller or an otherwise non optimal propeller. So the propeller's job is to convert the engine's power into useful thrust, and it does that by exploiting the shape and the rotation of the propeller blade. The propeller determines the load on the engine, and therefore it's an indirect consumer of fuel and a generator of emissions. So now, before we talk about, say, propeller damage or quality, let's also emphasize that you first need the right propeller for the ship. Propellers need to be matched to the ship's resistance curve, to the engine power curve, and the gearbox or the gear ratio. So getting the propeller size and specs right is the first job that we have to do. And we often see ships that require adjustments to the propeller size after sea trials have been performed. Um, Other scenarios for adjusting the propeller include replacing the engines, repowering, or modifying the hull. So sometimes propellers need to be adjusted to dial in operational requirements. Some examples of that might include adjusting towing RPM and speed for a barge train, uh, or maximizing fuel economy for a ferry. So whether you're delivering a new vessel or servicing an existing vessel, there's certainly a need to understand the propeller's geometry. And this is one of the reasons why propeller inspection, maintenance, and repair is just so important. Okay, so now let's talk about propeller quality. Now, any propeller that you inspect, even a brand new propeller, will have some geometric variance between each blade. And whether this variation was from the manufacturing operation, the delivery and installation of the propeller, or from striking something during the operation at sea of the vessel, this variation between the blades will have some effect on the propeller's performance. We'll just refer to these variations as damage for now. Again, even though some propellers may have been manufactured with some variance to start with. So damage to even a single blade will change the loading on the blade, and it will lead to more losses and more imbalances in the propulsion line. And that directly impacts propeller efficiency. Damage results in less thrust, in higher power requirements for the propeller, reduced operating speeds for the boat, and of course, higher fuel bills. Another common issue with uneven propeller blade loading is noise and vibration. Physically feeling and hearing the propeller at certain RPM ranges can be a very annoying problem for vessel operation. But beyond just being annoying, if it's left unrepaired, the propeller can also damage bearings, gearboxes, and engines all upstream from the propulsion line. And that's due to the eccentric forces that are created from differing hydrodynamic loads on each blade, and also the inertial imbalances of the propeller. So I think it's probably useful to just cover, how we describe a propeller. And the main parameters we use to describe propeller size are the prop's diameter, its nominal pitch, its blade area, which is usually expressed as a non-dimensional blade area ratio, or BAR, and the foil sections. Oops, sorry about that. Foil sections and associated camber in the blade. Um, to the propeller size is what provides the load on the engine. Sorry about that. The engine supplies the torque required to turn the propeller to a given RPM, and spinning the propeller at that RPM generates thrust that the hull needs to go a given speed. So therefore, propeller size gives us a direct influence on engine load versus RPM relationships and ship speed versus RPM relationships. And adjustments to the propeller frequently seek to correct performance issues. So when we inspect a propeller, we're checking the geometry of each blade to minimize the blade to blade variation. It's that geometric variation from blade 1, 2, 3, and 4 that alters this relationship between speed and RPM, engine load and RPM. And differences between blades or sorry about this. I guess there's some timing in the slides that I need to remove. Um, so differences between blades or damage to blades leads to reduced top speed, increase in fuel use, and damaging vibrations. Propeller inspection gives us pitch measurements for each blade, and we can average those pitch measurements from each blade together into an overall pitch for the propeller. The measured pitch can vary from its target pitch specified by the vessel designer, or the required pitch for the optimal performance of the vessel. And so to minimize those losses, we want to ensure that the pitch is close to the target, and that the variation of the pitch of each blade is within an acceptable limit. Propeller inspection, in some cases, or tuning and replacement, ensures maximum performance and efficiency. But how do we determine propeller quality? And how do we know how much variation is acceptable? Well, professional repair facilities use ISO 484, manufacturing tolerance for marine propellers. And this shipbuilding standard has long been the metric for inspecting both commercial and recreational propellers. The standard has four classes to gauge the accuracy of the propeller. The highest tolerance grade is Class S, described as very high accuracy, and that's typically used for motor yachts, cargo ships, research vessels, um, vessels that consume a lot of fuel and need a really efficient propeller. And from there, we have wider tolerance grades, Class 1 and Class 2, which are commonly used for workboats, tugboats, and ferries, and Class 3, which is just generally not recommended. It's kind of the minimum spec. Um, so the inspection methods outlined in ISO 484 are used to calculate the geometry for each blade by taking measurements at several different radial lines on the propeller. We'll see that coming up on the next slide. And that inspection method also checks the blade outline and the blade spacing to make sure that they're within spec. The other thing that the ISO tolerance specifies is the balance grade, the static and dynamic balance for the inertial properties of the propeller. So before we go in too deep here, I just want to give a little bit of background about our company here, TrueProp Software. We were formally established in 2017, and we create software tools and integrated machines to inspect propellers. And our goal is to provide our customers with the highest quality analysis, repair guidance, and compliance reporting, so that they can provide ship owners and operators with the best performing propellers possible. Now, traditionally, propeller inspection has been performed by propeller specialists who they have the equipment to handle, measure, and refurbish propellers, and that's our primary market. But today, I want to share with you some new technologies that allow propeller inspection to be more widely accessible. And shipyards, boat builders, and dry docks are now incorporating a 3D scanning process, or incorporating 3D scanning in general for a variety of QA processes. And the propeller shouldn't be excluded from this. So let's just, before we start talking about kind of the new contemporary approach, let's talk about how things are traditionally handled. So um, when there is a problem with the propeller or the boat is coming into dry dock, uh, typically the propeller will be removed from the ship and sent out to a specialist. So for large propellers, the propeller removal alone is quite a task. It requires a crew, it requires lifts and other special tools. And after removal, the propeller then needs to be rigged for transport and sent out, transported to a specialist off site. There's, of course, some turnaround at the specialist or the prop repair shop before the prop can be sent back, at which point it needs to be re-rigged and reinstalled uh, before it can be considered, you know, refurbished or inspected and ready to go. And in some cases, the prop may have been in suitable condition. It may have met its tolerance class, and it may have required very little work, to recondition. So, can you imagine the time and cost savings if we could just simply inspect the propeller without having to remove it from the ship? And so now we finally circle around to a solution. By leveraging commercial metrology equipment, such as handheld blue light laser scanners, we have a new versatile way to inspect the propeller without having to send it away to a specialist. We can scan the prop before installing it on the ship, which importantly documents the current condition, current propeller size and condition prior to delivery and sea trials. And in scenarios like maintenance dry docking, we can check the propeller's condition without having to remove it from the ship. We can check it right where it is, mounted on the ship in the dry dock. And the 3D scanners today are very accurate, as good or better than the probe-based measurement tools used by commercial repair operations. So if the propeller is found to be in suitable condition to return to service, this solution can bypass labor for removal, for rigging, transport, bypass costs at the specialist repair shop. Um, and you can get started inspecting props for your projects with just a 3D laser scanner and some technical software. And we offer a few different packages depending on the diameters of propellers you're looking to inspect. Basically, we can recommend a scanner for you and provide the modules needed to do the analysis. Um, so here we can see a larger propeller being scanned. And I want to point out that this technology can be used for propellers up to 160 inches in diameter. We've seen even larger ones done. It's also really great for controllable pitch propeller blades, propellers with overlapping blades, like you can see here in the root of this propeller. The blades are actually overlapped, which makes it very hard to get a traditional probe in there. Um, and our TrueProp software that you can see on the left side, it takes the 3D scan data that's captured by the scanner, and it extracts what we need to check the tolerances across the blade. It produces a report that documents the measurements, it documents the tolerances, and it shows us any errors, areas that are out of spec for that desired class rating. The software is widely compatible with any scanner that outputs an STL mesh. And we recommend blue light laser scanners, like you see the blue light flashing here. Um, although most blue light scanners require some small tracking markers, and you may notice them here in the video. If not, you'll notice them on the next slide. These commercial blue light scanners have become very affordable. They're very fast and accurate, and they can be used for lots of other projects, from checking running gear and shafts to mapping the engine room exhaust pipe path, uh, and mounting points for the engine. It's a general purpose engineering tool that we're just applying to propellers. And I wanted to show you a few more images here of the actual scanning process. Here we can see a large propeller being scanned, the left side here. This image is from Wildcat Propeller and being scanned by Daryl from Argonaut. And there's a little bit of overlap here in the blades between the hub. No issue for the scanner at all. And you can see these little tracking dots here that we use magnetic markers so that they're easy to put on and remove and reuse. Now, this other image on the right is from Pageant Swan Machinery, and this shows the scanning of a large CP blade. And by scanning the propeller blade to 3D, we can inspect that blade without the original hub or a dummy hub that would traditionally be used to fixture the blades for inspection. Instead, we can just orient the scan model in CAD and then analyze it. It's a really cool strategy. Scanning the propeller into a 3D model doesn't help you much unless you have the software layer to extract the necessary data and apply those tolerances. TrueProp helps do just that. It makes sense of the data, the 3D data that you get from the prop, and it shows you graphically where propeller tolerances have been exceeded. Now, measurements for each blade and each radial line are typically shown as bar graphs so that we can understand the deviation. I'll just zoom in over here. We can understand the deviation in pitch between blades, where the blade 1, 2, 3, 4, and 5 are shown here in different colors. These are different scribe lines at different radial positions. And so we can see here, this would be the root, and this would be going out to the tip, and things are good all within the tolerance boxes here. And as we get out to the tip, we can see some measurements that exceed the tolerance. And that's how TrueProp helps you make sense of this data. So if the variation fits within our tolerance band, all is well. But when it exceeds the tolerance, that's when we've identified some issue that requires repair work or refurbishment. TrueProp also automates the job management and reporting for your projects. It keeps all of your scan records in an accessible and searchable database, and that allows you to better understand the historical condition of the propeller before and after changes to it. So if a propeller needs to be replaced, all the data is there to source something with a similar size and performance. And by the way, this propeller here is a 120-inch diameter propeller, and it was scanned with one of the more affordable blue light laser scanners that's available today. So it's a testament to how far the technology has come, and how far prices have come down, that it's now much more accessible. Looks like I'm getting towards the end here on time, and so let me close by sharing some experiences from our customers. Cool Breeze Marine, it's a propeller repair company in the Ozarks, and this here on the left is George. He's using TrueProp to analyze the quality of a propeller he just scanned. And TrueProp allows George to quickly inspect the propeller. He does the repair work, so he repairs those blades back to their tolerance, and he's able to provide his customers with professional reports that document the state of the propeller before and after the work was performed. And to quote George, "We now have the ability to prove that the work is done right. Customers have complete confidence in us. TrueProp is the most accurate system on the market." And just one more testimonial from Pageant Swan here. TrueProp is efficient, effective, and accurate. It captures everything we need, everything we're looking for. Combined with our other technology, it generates reports very quickly as well. And that about wraps up the presentation. If this topic is interesting to you, if you have faced propeller problems or ship performance issues that may be related to the propeller, or encountered issues with propeller damage, really encourage you to reach out to us and learn more about what we might be able to do to help you basically eliminate some of those problems by undertaking propeller inspection yourself. And again, my contact information is here. So, and thank you all for your attention, and we can move on to questions and whatever else we might need.
Yeah, thank you very much, Adam. There's a couple of questions. First of all, I really like the presentation. I really like your software as well. I wish there were that kind of software. I wish it existed for every major component on a ship. The scan of it, the timeline of how it's changed over time, what to replace it with. I think other major components just get okay, apart from the engines, they don't get that kind of treatment.
Agreed. Yeah, absolutely. I deal with kind of upgrading solutions a lot, and a lot of people are coming from a traditional measurement approach where it's maybe it's got some sort of digital readout on it, but at the end of the day, they're handwriting down measurement numbers and calculating numbers themselves
Exactly.
on a piece of paper. And so by kind of introducing the computer to it and automating the process, it really improves the integrity and the ease of use and the accessibility and all that. So, you can scan the propeller and you can kind of compare it to a CAD model and get a heat map, but that really doesn't tell you much about the tolerances or the geometric size of the prop, and then
Yeah.
and that really corresponds back to performance.
Yeah, that CAD model comparison makes a lot of sense. We do have a couple of questions from the audience. So Pierre
Sure.
Adamopoulos from Kongsberg Maritime asks, can you scan underwater? And if so, what kind of accuracy do you think you could achieve?
Yeah, I love this question. So, because I often say I have a bullet, it says you can scan propellers anywhere, um, and I always have to put a little asterisk that says except underwater. So the issue with scanning underwater with lasers, one, water tends to be very dirty. Like there's a lot of particles floating in the water and stuff, and the lasers tend to capture that particle stuff. So you need special algorithms to then delete noise and stuff that comes from just junk floating in the water. The other issue is kind of the refractive nature of water kind of distorts the path of the laser as it's going through, and so this type of handheld laser isn't really great for inspecting things underwater. I've talked with a couple other people in the industry. It it might be possible to do. I know they're doing underwater hull inspections and things like that, and they're using photogrammetry to do that. So maybe a different type of scanner could address the scanning underwater. Right now, I don't have a solution for it, but the software on our side, all we care about is getting a geometric mesh, an STL file of the geometry out. So if there's a scanner that can work underwater that can produce that STL file, capture the geometry, then we can handle it.
Yeah, I
But
guess
yeah, right now I don't know a commercial tool that you can use to scan underwater.
Yeah, I guess you wouldn't be able to do that kind of comparison against the CAD model and get tolerances because it wouldn't be accurate enough. But it's probably, as you mentioned, there are people doing photogrammetry underwater
Yep,
for, I've seen it, for piers and stuff like that. It looks like you could get a good visual inspection that way. So you could get your 3D model, inspect it in the office for like a visual corrosion or, whatever, pitting,
100%.
fouling, that kind of stuff.
It's definitely something to be monitoring for the future, and one thing for large propellers, it's not too uncommon for them to actually put an enclosure around the propeller underwater and pump the water out. So they have a little air cavity to work in.
Yeah.
And in that scenario, it would be pretty easy to use this solution under there. The scanner itself has a battery pack, tethered cable, and typically we get a laptop like with us, very close by. Um, so you might have to bring your laptop underwater into that little enclosure, but with enough money, there's ways to get around these types of issues.
Yeah. Thanks. All right. One more
Good
question
question.
here from Vahid at Davie, Canada again. Could you inspect static or dynamic balance with this method?
So we do one thing that 3D scanning enables you to do is capture the full thickness of the propeller blade. So we can get basically a watertight model out that we could check moment of inertia in CAD software pretty
Mhm.
easily. The reality of bronze castings and nickel aluminum castings is they're not completely homogeneous, and so when you use a CAD model, you assume it's completely solid everywhere. I think there's probably too much variation in the material to accurately static or dynamic balance with 3D scanning alone. I think certainly tuning it. If you get if you scan a propeller and get a good class S tolerance level, there's a good chance that the balance is still probably in spec from when it was installed before. But yeah, great question. I don't think the technology is quite there yet to do it automatically.
All right. Well, thank you very much. I learned a lot there. It looks like a really good solution.
Yeah, yeah.
Yeah. Any more questions you can take offline. And I'm going to close this session and then come back more or less immediately on the same stage for a summary. So thank you very much, Adam. Thanks again.
Thank you for the opportunity. Thank you.
All right. Take care.
Take care.